Okay, I'll just use these same tabs and I'm going to go to workspaces, workshop, the AMR workshop, and we are going to talk about phylogenetic tree. And BV-BRC does phylogenetics in 3 different modes. One is bacterial genome phylogenetic tree, based on the components of the core genomes of bacterial genomes. Another way it does phylogenetic trees is for whole virus genomes. So viruses are small enough that you can actually align and do trees on whole viral DNA sequences, which you can't do for bacteria, and it wouldn't really make sense. And then if you're not into either of those whole genome phylogeny modes, you can do what we call gene trees, where you might have a set of genes and they might have paralogs and homologs from a variety of species, and you might want to do a tree on just the genes per se. So we're going to do bacterial phylogenetic tree right now, phylogenomic tree, so it's the whole genome. And one thing that we've got organized here is that there's a PDF in here that's easier for you to read that on the website to go through the exercises. And I've read it, and if I can remember it, I'm going to step through the step. If I veer too far aside, somebody shout at me and I'll try to get back on the path. We're looking at Haemophilus influenzae, and we're going to tree a variety of genomes of Haemophilus influenzae relevant to the phenotype of antibiotic resistance to ampicillin. So we're going to start a search in the search bar. We're going to search for genomes, and Haemophilus influenzae. So like if you can spell it, you're like halfway there. That's the hardest part. So here we have our genomes. How many genomes? Over 1,000 Haemophilus influenzae genomes. There's fewer than 1,000 when I did the search on my computer as my identity. So I think Rebecca has a lot of private Haemophilus genomes in here that are adding to the total. What we want to do is look at them and stratify them by antibiotic resistance to ampicillin. So look at the tabs. There's an AMR tab, and this is the AMR bacterial workshop. So it makes sense that we would be looking at this tab. Click on the AMR tab, and the columns change, and it talks about susceptibility and resistance to various antibiotics. And we can choose the antibiotic that we are interested in. We have to filter on ampicillin. You see that? There's the filter funnel icon, and then of the options you have for filtering on, ampicillin is the top one in the antibiotic column. So we'll filter on that. And there's 88 genomes with phenotype scored here. And if you click on the resistant, it resorts it by resistant. And I'm told that there are 16 in this resistant column. And if you shift click, you can like get that whole group of 16. We're going to take all of these genomes and we're going to make a group of them. I would do this, but Rebecca's actually already made the group, so I don't want to create redundant groups. But this is how you would do it. You click on this bottom icon in the action bar, and it's the group function, and you would create a genome group, and you could add it to an existing genome group or create a new one. And I would create a new one and give it a name, etc. Tell it what folder to store it in, but I'm not going to, because these groups already exist in the AMR workspace. So I'm showing you how to do it, but not actually doing it because it would be redundant. Then the other aspect for comparative purposes is we were going to grab 16 for balancing it out, susceptible genomes. And we would create a group with those as well. But I'm not going to do that either. And there was one more genome group that Rebecca wanted us to include, and that was to be sure to include Okay, finally, I got it. I'm going to create a group with that one. I'm just going to create it in your genome groups thing.
Is that public?
Yeah, this is a public genome.
Yes, it's totally public. There's a reason we're including this, so you can see what happens when a job fails. So this one is destined to fail.
So now we've got the groups that we're going to build the tree from. That was all setup work just to get where we need to go for building the tree. I'm going to go back to the workshop folder, to the phylogenetic tree subfolder. And now you'll see that we have these two. Oh, we don't have the 16 resistant. I don't care. I'm going to create a tree with the 16 and the 72. So I'm going to go to Tools and Services, and the phylogenetic functionality is all clustered at the very bottom left side of the Tools and Services dropdown. And the upper one is bacterial genome tree. We're going to do bacterial genome tree. And this is a similar input motif to what you've seen before. And what we can do is use this box to select genome groups, right? Here's this one that I just created, and that was easy because it was defaulted into the genome groups folder, which is where Rebecca, the input, gives us a warning and wants us to not input this genome into the analysis. Did you see that?
Say that's cool.
It says, this looks like an invalid genome group. The following errors were found. Plasmid genome.
I could look to see what you named it, actually, because my friend here, who's already submitted the job, he put it in select genome to get there. Let me read it to you. In that top box, put in 727 dot. If you see the plus there, now add that. Now click on the down arrow.
Okay. Okay, that's susceptible. I'm just going to add those even if it's and resistant, even if it's more. So we have our susceptible and our resistant and our one special genome that we've jumped through hoops to get in here. Then other controls that you have on this entry box specify parameters that are going to control how the tree is made or how much computation and data goes into the tree. And you can specify how many single copy genes you want concatenated into this giant alignment, the data alignment that's going to be used for phylogenetic tree building. And it defaults to 100 genes, and that's quite a lot. But
Wonderful.
If you want very strong trees based on bootstrap support, you frequently do need to go to high numbers of genes, even 500 or 1,000. You know, it takes a long time. It might take like a day or something to run a tree with 1,000. In our case, I'm just going to click on 20 because that'll be plenty for demonstration purposes for this particular example. Other parameters here are numbers of instances of a gene family having an extra copy. So like for the genomes that you have, it's going to search for perfect single copy genes that occur once and only once in each genome. But these numbers are little fudge factors which allow it to accept a gene family that's near perfect, except that it has one extra copy of the gene in one genome, or 2 extra copies, or 3. I'll let it be a little less stringent in its definition of single copy genes, or be missing a gene in one genome or in 2 genomes. And frequently a genome is imperfect and it doesn't have actually all of the genes that, you know, if you had more sequence, more read data or something, you would have gotten absolutely all the genes. So missing a gene is not bad, and it's not going to really be too detrimental to the tree. But we're going to leave those as 0 and 0.
But they should do their jobs that they created today.
That's right. We have our workshop folder. And I'm going to submit. So the job's been submitted. And if you look down in the jobs box in the lower right, I don't know if people indicated the meaning of these numbers down here. The leftmost number is jobs in the queue. Sometimes there's a lot of jobs submitted, and when you submit a job, it goes in the queue and it stays in the queue for quite a while you're waiting for it to go into processing of your personal jobs. The next number in the middle is your jobs, how many are currently running, and 3 jobs are currently running. 2 jobs were running before we submitted that one. And on the right side is just how many completed jobs you have. And she's got over 5,000 completed jobs. So what we want is for that middle number to drop down to 2, because 3 means that this current tree job is still running. I'm going to submit the susceptible, add, and the resistant, add. And I'm going to leave it at 100 genes. You think 100 genes is good, Rebecca?
That's will be a question we'll ask to see it, right?
I'm going to increase these numbers to 1 each just to give it a little bit of leeway. And then there's the UVA output folder, and then the output name is Haemophilus influenzae, AMP, resistant, and susceptible tree. Submit. So I want to see that job number go up to 4. Now there's 4 jobs running. And I don't know, Rebecca, if we go to that folder, we'll...
Needed jobs.
Okay, let's go to the phylogenetic tree and look for the pre-run jobs so we don't have to wait for those. First, we're going to look at this one. This is the result of the tree job, including that special genome. And this has the view icon at the top that shortcuts to the best way to view the results of this, which is the which doesn't result in much because, in fact, there is no tree. This is scanty output you'll see when comparison to it. Luckily, you'll notice that this bottom file is .html, and HTML files are intended to be easily interpretable in a web browser. So I'm going to click on the icon here, or you could click on the view icon over in the action bar. And the HTML report will kind of explain the job, tree analysis statistics, requested genomes 33, genomes with data 33, max allowed deletion 0, 0. Single copy genes found is 0. We requested 100, but we got 0. And it took 0 seconds to align them because there were no proteins to align. And then this next table down tells you for each of the genome IDs, how many total genes did that genome have, and how many were single copy, and how many were used in the analysis. And this top genome only had 4 genes. And so that genome was a plasmid, and that was the trick or the reason for including it, because this is a trip up that frequently happens, and we just wanted to expose more of you to this potentiality so that you would know how to deal with it and you'd be able to recover gracefully from it. If you scroll all the way to the very bottom, in cases when the tree fails to find enough single copy genes, it suggests to you genomes to omit from your analysis, and it would increase the number of genes that would count as single copy. Since we used 0 for how many, the leeway that where a gene could be missing or present in 2 copies, if we had increased that to 1, it would have actually run and it would have been fine. It would have omitted that plasmid genome and life would have been much more normal. So that was an example of what not to do.
Or once you get it, because I get a lot of tickets about this. My job didn't produce a tree. What happened? And right there it tells you.
Read the HTML report.
Right, you have the plasmid genome, and it's always plasmid genome. Every single time.
And
don't use plasmids.
Look for the one that has very few genes, and also scan to the very bottom, and it will suggest genomes to omit from your analysis. and it will improve the number of single copy genes that qualify as single copy.
So here's a question to the group as a whole. What's wrong with plasmid genomes? Why can't we? Could we make a tree with plasmid genomes? What's so special about them? Why are they not good for these type of analyses? It's because they're small and the genes on them are generally not broadly shared. They're very unusual. So when you're bringing them against a lot of other bacterial genes, often they don't include plasmid. So there's not going to be any way that you can have enough to generate a tree unless you do things beforehand to see how many genes are shared across those. So it can be done if you're clever, but just going there from the very beginning, you'll have problems.
Okay, now let's do it the right way. You should have your own tree being constructed right now. We have this job output from a previous run of this very same job. And now you'll see that there's more files. There's like twice as many files as there were in that first job that didn't actually generate a tree. And now when you click the eyeball icon in the top right, it actually can show you the tree. And we have a tree viewer called Archaeopteryx. It's written by one of the members of the viral half of the BV-BRC. It's a little bit peculiar and it has a lot of capabilities. One thing is that there's this floating menu here. I like to move it sort of over here to kind of get it out of the way, but it's very useful because you can highlight and color highlight genomes based on different properties that they have. It's a nice looking tree. You can zoom out and in. It's kind of cool on that regard. It's got the bootstrap support values written on the branches of the tree. This is based on 100 genes. I would say that's a very strong tree, but bootstrap supports are only like in the 40s down here at the base of this kind of clade over here. If you really cared about these particular genomes in the tree, you might run it with 500 genomes or 1,000 genes.
What do reviewers look for?
Well, I don't think that there's a threshold. There's not a magic number. And as Jim pointed out earlier, 5 could be a fine number for the purpose.
Get the bootstrap values.
Oh, well, the bootstrap values are where you can see the weakness and or strength of your tree. But you know what? Depends on what the scientific question is. You might have a question that those bootstraps, that weakly supported branches are not relevant to the scientific question you're asking. So it depends. Sometimes you really care and you can crank up the data to higher levels and get your bootstrap supports really high, but you don't always have to. You don't have to get all your bootstraps to be 100% to be happy with your tree. This is using midpoint rooting, but you can reroot the tree if you want to using, there's a special menu that you get when you click on the node, and you have to be very precise with your clicking. You have to wait for the cursor to change to the hand icon, and you can reroot the tree at that point. I don't think I want to because I'm not sure I can get it back to its normal shape after I do that. I'm not going to do that right now. One thing you can do when you're hovering over a node is you can select all the descendant nodes. And so there I've highlighted in red all of the descendant nodes from the node that I clicked on. Having done that, it interacts with the action bar such that you can create a genome group, or you can also click on the one above it, which is the genomes, and that takes you, it creates a new tab, and it shows you genome information for those particular genomes. Or creating a genome group is another option you can have. I'm going to unselect those. So one really great functionality here is being able to color highlight your genomes based on metagenome properties. And the ones that we have here are collection year, genome name, which doesn't make sense to color highlight, isolation country, and I'm going to try that. And wow, that's interesting.
Yeah, it was part of one big study from Portugal.
Oh, okay. Well, so all the ones that have metadata on isolation country are from Portugal, and there's three without isolation country data. And let's just try a year just to see a different option. So color highlighting makes sense if there's a manageable number of discrete classes. It doesn't make any sense if every tip has a different value for a particular field, or if all the tips have the same value for a particular field.
And it only makes sense if it supports the story. Every publication that you write, it should be telling a story. And you're trying to convince the reviewers that this is a true story. So you want the figures to support the story that you're telling. And this story of the years wouldn't help.
But one could imagine if there was an outbreak scenario, perhaps that the time of the collection would be very relevant to the story you're trying to convey. I'm going to go back to the BV-BRC workshop, back here, back to phylogenetic tree, and show you a tree that is not output, a color highlighting that we wished, that we hope, we aspire to be able to provide you, that is relevant to the subject of today's workshop. And that is this one. It's too big and it doesn't fit right, but this is a whole lot of Haemophilus genomes with genomes resistant to ampicillin highlighted in red. Now, we do have antibiotic resistance phenotypes in the database, but as you could tell from briefly, when I was searching for the Haemophilus influenzae genomes susceptible and resistant to ampicillin, there was some complexity to that data structure because there's different antibiotics. So there's complexity to that data structure that makes it difficult to be able to manifest that data directly onto a tree without a whole lot of work. Rebecca went to that work for color highlighting the nodes on this tree, but she did that manually in some other software. So we hope to be able to show antibiotic resistance as a phenotype on the tree. So that's one thing that we wanted to get.
But the take-home message here is that ampicillin resistance doesn't cluster together on the tree.
Look at that. It's just a couple, it's a few genomes here, a few there. Yeah, it's not like one clade on the tree has all of the resistance. So each one is like picking it up in some weird individual unique way. So that's phylogenetic trees asking the question, does phylogeny explain ampicillin resistance in Haemophilus influenzae? And the answer is apparently no. It's distributed across randomly or haphazardly across the phylogenetic tree and not highly clustered. I think I hit the highlights. I don't think I went into all of the gory.
You know how to download the SVG of the trees.
Luckily, in this viewer, we had the breadcrumbs fixed up so that you can go back to the job results folder level on the tree output, going through the different outputs. There's the SVG, which you can just sort of look at, and you can download this. And this is scalable graphics, so you could load it into an SVG editor, and you'd be able to change the font on the.
Go back to Archaeopteryx again, because I find that this particular SVG.
I'll do that in a different. Let me just do it here. And I'll do it this way.
Because, you know, if you had metadata that you wanted colored or something, just like color the whatever, it doesn't matter.
The year.
Just for pretending that means something. You can download this as an SVG.
Which I'll show you where to do that right here.
Before you do that, I always find that the lines are really heavy in this.
Oh, you can control that.
Bigger. So you can control that to make a more pleasing figure. I'm all about the figures, creating the nicest figure for your publication. I would play with these. I always upload the SVG and Adobe Illustrator. I like that, but you could also use Figtree and manipulate it that way to give you a really good figure for them. Here you can download, it says PNG, and at the very bottom you can get the SVG.
There's controls to increase the y-axis or shorten the y-axis, or increase the x-axis or shorten the x-axis.
Right now we limit it to 100 genomes to run the whole thing, but for the viral genomes there's a lot more. But generally, for me, especially with the bacterial stuff, I'm always thinking about the publication and how this is going to look in a publication. And if you have 100 genomes, often it's very hard to see that figure. So I generally like 20 to 40, I think, will be something that can be resolved well.
One thing you can do is collapse a whole branch on the tree to a smaller thing. So that would be useful for showing a very large tree if you wanted to edit that by collapsing certain branches on the tree.
Oh, I didn't realize that was fun.
Yeah.
So then you could have a bunch more and then just, then you wouldn't have to rerun it. So this is a powerful little piece of software for this viewer, but it takes some manipulation.
One thing I didn't mention is that the tree is built from a combination of the aligned nucleotides and the aligned amino acids. Uses the program RAXML.
So up one is the thing, that reminds me.
To the report.
Okay. Scroll down.
So it starts off with a mini graphic generated by Figtree.
Okay, so stop right here. Often if a reviewer asks, they'll say, you built it on 100 genes. And some reviewers will say, okay, what 100 genes? Or, they'll get, to me, that's reasonable when it's 20 or something, but if it's 100. But the good thing is, before we go there, look at the number of amino acids aligned there, that figure, and the nucleotides.
Yeah.
That you can embed that right in the results section of your paper or in your thesis or whatever to tell these what this tree is based on, this number of amino acids, this number of alignment. Step one up again to the report. And so this is what I've done. When someone asks could you go into the details?
Yeah, there's a folder here, and it's got even more files. Luckily, we spared you having to see these by hiding them away. One thing is, if you really wanted to know what genes were used in the alignment, you could look at this file.
Get a list of all those genes. And I once had a tree that was based on 1,000 genes for the publication. One of the reviewers said, oh, what genes? And this you can just download it as an Excel file or as a text file, and you can put it in the supplementary information, and that will quiet that reviewer. You will not hear anything more about that tree or that.
If you needed the Newick file for the tree because you were going to analyze the tree yourself doing some other program that wanted the Newick file, that's right there. For example, to load into Figtree to generate graphics. One thing about the report is it tells you how long it took for the different steps. The RAXML time took 1,087 seconds, and the whole analysis took 1,336 seconds. For the protein analysis, there's different protein substitution models, and what it does is it searches through all of the available models and it selects the one that has the best statistics. And oddly, in this case, that protein substitution model is called Dummy 2, which isn't a really inspiring name, but that is a valid protein substitution model. Usually LG turns out to be, it's very frequently the protein substitution model.
Does that have the version of RAXML? It should tell it somewhere. Because I've actually had a reviewer ask me that too. what version of Chrome was used.
Perhaps.
And they were kind of snarky when they said it.
Oh, the version, yes.